Dear students, the last section in this semester was saying that after this one I should say goodbye. It's talking about the integral of one ln and e to power x and something else. So in general we have a differential of the non-zero fractional things like that. We say we have a ln of x, for example. If I have 1 over x dx, there is no way to say I'm going to bring this one to up and I say dx, then I say plus 1 minus 1. You know why? Because you'll get x to power 0 over 0, which is not right. So for that, about that, we have what? We have another rule. You see, if you have a u in the denominator and du in the numerator, here's u, here's the du, then you can say ln of u plus c. For example, I have 1 over x dx. The derivative of dx is equal to dx, just 1. So I have the derivative. So that's why I say what is equal to ln of x plus c. How about in case if I have, for example, 1x squared plus 5x, and here I have x plus 5 dx. In that case, you know that the derivative of denominator, the derivative of here, is equal to x plus 5, because we have du, here's the u du, so that's why I can directly say is equal to the ln of denominator without any hesitating. Just write like that. Okay, dear, just ln of the denominator. That's all about these two examples. Example 3 is easy. You have a 2x, so you have directly, I can say that. In case you have a, for example, you have a, what you can say, you have a definite integral. You know, we have 2x, so that's why I can say is equal to ln of x squared minus 5 from what? From 0 to 2, there is no c. And you know, first we should put the 2 squared minus 5 minus of the rule 0 squared minus 5. Okay, so in that case I will get what? 4 minus 1 minus 5 is equal to minus 1, so ln of 1, and minus 5, ln of minus 5. And you know ln of 1 is equal to 0, and ln of 5 it remains, so it's equal to minus ln of 5. That's all that you need to know about this example. He changed to this one, do not care about that. Please try to follow my method. He changed, he made some substitution. That's why the boundary changed from 2 to minus 1 and from 0 to minus 5. Don't care about this one. Now it's time to finish the integral of the triangle inequality without rules. When I say without rules, for example, you know the sine of x dx is equal to what? Is equal to cosine of x plus c. And you know the derivative of integral of the cosine dx is going to be sine of x plus c. And also you know something else, we have no tan. We don't know tan of x dx is equal to what? We have no direct. Maybe you see something is equal to tan. I am just remembering you, it wasn't something, it was secant square x dx is equal to tan x plus c. But we haven't the direct method say tan is equal to something. So for solving this one, you know, the tan and cotan, they are both are the same. For tan, I am going to solve the tan, and I'm leaving this one as a homework. So for tan, you know, we have equal, you know, the tan is equal to sine over cosine dx, and you know the derivative, because I have a fraction, the derivative of denominator, derivative of cosine is what? Is equal to minus sine. So that's why I put minus here, minus outside. So the result will be what? Minus denominator cosine of x plus c. And in your book you change like that. Okay, you know it's equal to ln of what? 1 over cosine of x plus c, and you know 1 over x is equal to secant of x plus c. That's why you have a second here. So in that case, you know how to solve sine over cosine, and why you get the second here. So in general, how about cotan? How about cotan of x dx? You know, cotan is equal to cosine of x sine of x dx, and the derivative is x, so is equal to sine of x plus c. It's easy. You can see that. It's very easy. Now it's time to solve the another things here. How about instead of, if I have second, so number 5, if I have second of x dx, do not forget that we don't have this one directly, but we have second x tan x dx is equal to second x plus c. We have this one, but we haven't second in just only directly. So that's why for the second we need something method that also we don't know, you don't know before you see it. We multiply this function by second of x plus tan of x over second of x plus tan over x. You know, in mathematics you can cancel this one, I get 1, so nothing happened. We just multiply second by 1. But why we change it to this one? Later in the next step you know why we bring this one and why we multiply. Now numerator to numerator, second square, we will get plus second x tan x, you know, and the denominator second x plus tan x dx. Do not say we can distribute. There is no way, because this one together. So now it's time to know why we multiply by this one, because you know the derivative of second is equal to what? I have a fraction. So in the fraction, if it's easy, I'm bringing it to up. If it's not easy, I'm thinking about u du to get the ln of u. Okay? So in that case, you see the derivative of second is equal to what? Second tan. How about the derivative of tan is equal to second square? So the derivative of here, u, is exists here, du. So that's why I say is equal to second x plus tan x plus c by ln method. So this is the really tricky way, because before you multiply this one you get the result. How about the number? This is the number 5. How about the number 6? If I have cosecant x dx, you should multiply by what? I'm just telling you, you should multiply by cosecant cotan of x cosecant cotan of x, and then you have the same steps here. You can see these examples in page 14, and also you can find the the cosecant in the page 16 in your 5.5 section of 5.6. Now here's the brief case of the box that give you the brief methods. You know how to get that one. It's time to solve this one. We have what? Number example 4 in page 15. Sorry. Page 15. So this one's the page 15. Don't forget. I made a mistake. So we have example 4 in page 15, section 5.5. We'll say that we have what? We have from 0 to pi over 6, but we have tan. Do not forget you have an angle here. You have an angle here. You know, this one is equal to what? This one is equal to sine 2x over cosine 2x. Don't forget about the x, the angle. And the derivative of here is equal to what? Is equal to minus sine 2x multiply 2. You know why? Because I have an angle here. I told you, if you have a triangle and the angle, you need the derivative of the angle. So here you need 2 and 1 over 2 here. Okay, dear? So minus minus for the cosine, 1 over 2 for the angle. So directly you can say is equal to ln of the denominator. Okay? How about minus 1 over 2 here? That's all. But we have what? We have from 0, okay? We'll delete this one, from 0 to pi over 6. Just try to put the pi over 6 here. So you get what? You get cosine 2 multiply pi over 2, pi over 6, sorry, minus ln of cosine 2 multiply 0. That's all you have. You can do it and you can find that. How do you say that? Result. Here's the big another important thing. So we have we finished the first part, which they are very important. This means 1 over u du. You will get ln of u plus c. Now the second part is what is about the exponential integrals. So the integral of the exponential is that if you have a e with hat and du, so directly you can say you have eu plus c. So here's the important relation between where and where? Between u and du. So e, they do nothing. Just we'll put it here. So of course I'm going to start with the easy example. So derivative of x is equal to dx. So that's why I say x plus c. How about this example? E to power sine of x cosine of x dx. You know this is the u. So find the derivatives exist or not. So derivative of sine is equal to cosine dx. So that's why we say is equal to itself plus c. Nothing happened. Okay. How about in case we need, for example, something else like e to power 3x, for example, dx. Which is example 3, page 15, 5.5 section. Okay, so how we solve this one? You know the derivative here, e to power d. So the derivative of 3x is equal to what? Is equal to 3. But we haven't 3. So I'm going to put 3 and for number it's okay, but for the variable you cannot solve it. So 1 over 3 e to power itself is equal to itself plus c. That's all that you need to know about the integral. And in case you have a boundary, do not change please. I'm going to solve this one for you. So from where to where? From the 0 to ln of 2. How we solve? We say 1 over 3, okay, e to power 3 ln 2 minus e to power 3 multiply 0. That's all. So is equal to what? 1 over 3. And ln and e will cancel each other. So and this 2 is coming to here, so is equal to 2 to power 3. And e to power 0, 3 by 0 is equal to 0. So e to power 0, like a number, is equal to 1. 8 minus 1 is equal to 7 over 3. That's the result. Okay, dear. So please do not follow the book's method because he do something substitution. You don't need it to make it more complicated. Just do it slightly, and you will get the result which is easier than the previous one. In general case, so last page, yes, page 16. We have what? We have another rule. So the same thing look like what? This one's look like e to power u du. Am I right? It's equal to e to power u plus c. But here let's change it. If I have a to power u du, means that the hat and the derivative are equal. So I will get the a to power u plus c, but here we will put the ln of the base. For getting more information, before we have x dx, now I have 2x dx, which is equal to itself plus c. Now here I am going to say itself plus c, but I am going to add the ln of the base. That's all that I changed here, and nothing happened. So how about 2 to power sine x, for example, and cosine x? Cosine 2 to power cosine x sine x dx. You know this is the u and this is the du. We will check. Derivative of cosine is equal to what? 2 minus 2. So that's why we will get itself plus c. That's all that we need to know about this function. This is the example 5 in page example 5 in page 16 section 5.5. Okay, dear, that's all about what we have. Example 6, there's an idea in it. It's a log of 2x over x dx. We didn't mention how to solve the log, so that's why I say there's an idea. Here for the log we cannot solve the log, so we have the rules say log of, for example, 2x is equal to ln of x over ln of 2. Okay, this is the rule, law rule. Okay, so that's why we change the log of x over log of 2, sorry, ln of x over ln of 2 over x dx, and this one will change. 1 over 2 will come to inside the number, so ln of x over x dx, and you know ln of 2, 1 over ln of 2 is the number again. You know ln of x and 1 of x, there's a relation between them, right? So this is a u, and how about this is du? So inside, outside, careful. So I know it's a special case. So that's why, because the derivative of inside exists, so I say is equal to ln of x to power 2 divided by 2 plus c. Okay, because as you have also in your exercise, for example, another example, if you have ln of x with x dx, you know this is what we have, u and we have du. So inside, outside. That's why we will add, we say is equal to ln of x to power 3 over 3 plus c. Okay dear, that's why it happens something here. Maybe it's strange for you, but this example, extra example, will help you for understanding. Now I'm going to leave this example for you. There are this ones, we solved that one a lot. This one I just need to add one step, so please read it as a homework, and it's the last day, so I am happy to teach you this course. Inshallah, see you in the calculus 2 or with any other lecturer. I hope you will find this course as which is very really intensive, and it's a very quick in this case, pandemic COVID-19. You know, we all at home. Hope you are safe and hope you are studying well, and you will pass in the final exam. See you all, and wish you all the best. Thank you very much for being with me. Thank you for preparing every homework and assignment and report with me. See you in the next stage with good health. Bye for now. Our lecture was finished, and good luck.